Line operations safety audit utilizes trained observers riding in cockpit jump seats to evaluate several aspects of crew performance. At the core of the LOSA process is threat and error management, or TEM. LOSA data sources provide airlines with a diagnostic snapshot of safety strengths and weaknesses in normal flight operations. Today, LOSA is recognized as an FAA voluntary safety program and is considered by several other aviation organizations such as CAA and IATA as an industry best practice for normal flight operations monitoring. The structure of this presentation is to discuss a bit of the theory behind the concept, the method used for the LOSA project at SAA, and finally to talk about some results. The LOSA archive is a database containing observers' narratives and coded observations from all the airlines that have conducted a line operations safety audit with the LOSA collaborative. Because of the stringent quality assurance process, results from different airlines can be pooled to derive industry averages. The LOSA archive can also benchmark an airline's performance against other airlines, providing a multi-airline context for understanding an airline's strengths and weaknesses. Based on the success of Continental as well as other LOSA carriers, the International Civil Aviation Organization, ICAO, made LOSA a central focus of its Flight Safety and Human Factors program and endorsed it as an industry best practice for normal operations monitoring. The ICAO LOSA Manual Document 9803 has a reference in this regard. The Federal Aviation Administration also endorses LOSA as one of its voluntary safety programs. As a result, TM and LOSA are now recognized worldwide. Threat and error management is a systems approach to aviation safety, originally developed by human factors researchers at the University of Texas. TM offers an intuitive and flexible approach to practical risk management. TM not only offers a framework for understanding and directing human performance in complex operating environments, it also provides aviation professionals, regardless of their organizational function or status, a risk management lexicon that supports a positive safety culture. The easiest way to understand threat and error management is to liken it to defensive driving for a motorist. The purpose of defensive driving is not to teach people how to drive a vehicle, example, how to shift a manual transmission, but to emphasize driving techniques that people can use to minimize safety risks. Similarly, TM does not teach pilots how to technically fly an airplane. Instead, it promotes a proactive philosophy and provides techniques for maximizing safety margins despite the complexity of one's flying environment. In this sense, TM training can be framed as defensive flying for pilots. TM proposes that threats such as adverse weather, errors such as a pilot selecting a wrong automation mode, and undesired aircraft states such as an altitude deviation are everyday events that flight crews must manage to maintain safety. Therefore, flight crews that successfully manage these events, regardless of occurrence, are assumed to increase their potential for maintaining adequate safety margins. It is this notion that provides the overarching objective of TAM to provide the best possible support for flight crews in managing threats, errors, and undesired aircraft states. TM begins with a single question, and a simple question though. Do the concepts taught in training transfer to normal everyday flight operations? A threat can be defined as events or errors that occur outside the influence of the flight crew. Using this definition, a threat can be, for example, high terrain, icing conditions, and aircraft malfunctions, such as an inoperative thrust reverser, or other people's errors, such as an inaccurate recording of fuel load by a dispatcher. All these events occur independently of the flight crew, yet they add to the crew's workload and need to be managed. Sometimes they can be managed discreetly, and sometimes they interact with one another, further complicating the necessary management. In commercial airlines, threats can be divided into two categories: environmental threats, which are outside the airline's direct control, and such as weather and ATC, and airline threats, which originate within flight operations, such as aircraft malfunctions and ground problems. Threat management can be broadly defined as how crews anticipate and or respond to threats. A mismanaged threat is defined as a threat that is linked to or induces flight crew error. Some of the common tools and techniques used in commercial aviation to manage threats and prevent crew errors include reading weather advisories, turning weather radar on early, thorough walkarounds, and during pre-departure, etc. An error is an action or inaction. Flight crew errors can be divided into three types: aircraft handling, procedural, and communication errors. Aircraft handling errors are those deviations associated with the direction, speed, and configuration of the aircraft. They can involve automation errors such as dialing an incorrect altitude, or hand flying errors such as getting too fast and high during an approach. Procedural errors are flight crew deviations from regulations, flight manual requirements, or airline standard operating procedures. Lastly, communication errors involve a miscommunication between the pilots or even between the crew and external agents such as ATC controllers, flight attendants, and ground personnel. Error management is now recognized as an inevitable part of learning, adaptation, and skill maintenance. Hence, a primary driving force behind TM is to understand what types of errors are made under what circumstances and how crews respond to those situations. In those situations, the heart of error management is detecting and correcting errors. However, approximately 45% of observed errors in the LOSA archive were errors that went undetected or were not responded to by the crew, which give credence to an important point for effective error management. An error that is not detected cannot be managed. An undesired aircraft state, or UAS, is a safety compromising state that results from ineffective error management. Examples include unstable approaches, lateral deviations from track, firm landings, and proceeding towards the wrong taxiway or runway. Events such as malfunctions or ATC control errors can also place the aircraft in a compromised position. However, in the TEM taxonomy, these events are considered threats as they are not the result of actions by the flight crew. As with errors, UASs can be managed effectively, returning the aircraft to optimally safe flight, or mismanaged, leading to an additional error, undesired aircraft state, or worse, an incident or accident. Similar to this crocodile, the LOSA can be seen in this flight operation safety envelope. The green area or portion of the flight safety envelope is where normal operations take place, such as aircraft flying Joburg-Durban, Durban-Joburg in normal situation, no incidents, nothing that's undue in the operation. In the yellow area, this is where we get the incidents if anything out of the normal procedure or normal flight occurs. And in the red portion, accidents. So a LOSA would fit in the green portion of the flight operations safety envelope, which is a snapshot of normal operations, whereas incidents are normally monitored by the flight operations quality assurance systems, and of course accidents take place in the red portion and an accident investigation takes place. Similar to this crocodile, a threat could be overt, that is very obvious, or hidden, that is latent. Active and latent threats are the precursors to accidents and incidents. Most threats, however, can be proactively identified through LOSA and considered as targets for enhancement. So a threat may be minor or major, and when managed correctly, inconsequential. If the threat was not managed, it can lead to a threat-induced incident or accident. For instance, a maintenance error not picked up by the crew can lead to such an incident or accident. Crew may incorrectly manage a threat leading to an error. LOSA considers three possible responses by crews to errors. Trap, in which case the error is mitigated and the event inconsequential. However, if the error is exacerbated or there is a failure to respond to the crew error, it may lead to an additional error or an undesired aircraft state, which may both lead to an error-induced incident or accident. A LOSA observer therefore actively records these threats, errors, and undesired aircraft states on each flight sector. LOSA is therefore a proactive safety data collection program. The data generated provide a diagnostic snapshot of organizational strengths and weaknesses. So the next step is, once we've understood the threat and error management model, the next step is actually implementing the LOSA. However, LOSA is actually defined by 10 operating characteristics. If it does not have these 10 characteristics, it cannot be considered a LOSA. Jump seat observations during normal flight operations. LOSA observations are limited to regularly scheduled flights. Line checks, initial line indoctrination, or other training flights are off limits due to the extra level of stress put upon the pilots during these types of situations. Joint management pilot sponsorship. In order for LOSA to succeed as a viable safety program, it is essential that both management and pilots, through their professional association, if it exists, support the project. Voluntary crew participation. One way to accomplish integrity is to collect all observations with voluntary crew participation. De-identified confidential and safety-minded data collection. LOSA observers are asked not to record names, flight numbers, dates, or any other information that can identify a crew. This allows for a level of protection against disciplinary actions. The purpose of LOSA is to collect safety data and not to punish pilots. Targeted observation instrument. The current data collection tool to conduct a LOSA is the LOSA observation form. The instrument used for the CAA LOSA was constructed from the source theory and enhanced for our particular needs. Trusted, trained, and calibrated observers, primarily pilots, conduct LOSAs. Observation teams will typically include line pilots, instructor pilots, safety pilots, management pilots, members of human factors groups, and representatives of the safety committee of the pilot's organization. Another part of the team can include external observers who are not affiliated with the airline. However, for the LOSA conducted at CAA, we utilized only line pilots. This gained the trust from the pilot body. Trusted data collection site. In order to maintain confidentiality, airlines must have a trusted data collection site. We gained support from the University of Pretoria to monitor the collection of data. Data verification roundtables. Data-driven programs like LOSA require quality data management procedures and consistency checks. For LOSA, these checks are done at data verification roundtables. A roundtable consists of 3 or 4 department and pilot association representatives who scan the raw data for inaccuracies. Data-derived targets for enhancement. Here, patterns of error are identified for the airline as LOSA targets for enhancement. And feedback of results to the line pilots. After LOSA is completed, the airline's management team and Pilots Association have an obligation to communicate LOSA results to the line pilots. Pilots will want to see not only the results but also management's plan for improvement. If results are fed back in an inappropriate fashion, experience has shown that future LOSA implementations are welcomed by pilots and thus more successful. So these are the 10 operating characteristics of a LOSA, and if each one of those 10 characteristics are met, an airline can consider the audit or the check on normal line operations a line operations safety audit and not some other check or audit as such. At present, CAA operates a fleet of 24 long-haul Airbus 340 and 330s, 11 Airbus 319s, and 13 Boeing 737-800 aircraft, 319s and 2 320s at the moment. There is also a dedicated freighter fleet that consists of Boeing 737-300s and 400 aircraft. The route structure consists of both domestic, regional, continental, and intercontinental destinations. The size of each fleet therefore suggested to us the proportion of sectors. This in turn was used as a starting point to determine the number of LOSA observations. The so-called bell curve shows that the majority of observations came from the Boeing 738 fleet, followed by the A319 and A340 and lastly 737 freighter fleet. By comparing the actual selected distribution of observations against the normalized distribution, appropriate statistics was used which would best infer characteristics of South African Airways flight operations. It was determined that a total of 134 sectors would be sufficient to gain an accurate cross-sectional or post hoc observation Here, the goal was the discovery of the range or extent of latent and overt safety critical conditions in SA's flight operations. After completion of this phase of LOSA, 137 observations were conducted. Our LOSA project took around 2 years to plan, and the observation phase was completed within 3 months. It took a further 2 months or so to clean the data and present recommendations to the relevant parties. Next, I want to briefly discuss some results from the SAA project, which you may find of interest. A total of 137 sectors was observed during the LOSA period, and the table describes the distribution of observations per fleet, with 77 observations taking place in our Boeing fleet and 60 on our Airbus fleet. Additionally, the sample consisted of 274 crews. The average experience level of the captains involved in the study was 15,365 hours, while in the case of first officers, the mean experience level was 7,362 hours. The mean experience level of pilots operating advanced aircraft was around 11 years. A total of 514 threats were logged. This equates to a threat prevalence rate of 3.75 threats per sector. It appears from this data that the number of threats managed by our crew per sector were on average more than the global norm. Environmental threats totaled 66%, whilst airline threats totaled 34%. The number one threat to the organization's operations stems from ATC. This includes challenging clearances, late changes, ATC errors, language difficulty, non-standard phraseology, radio congestion, runway change, similar call signs, etc. Thereafter, adverse weather such as crosswind, tailwind, gusty conditions, high winds aloft, icy conditions, IMC thunderstorms, turbulence, and wind shear, followed by airport threats, which examples of airport threats would be airport construction, runway contamination, lack of or faded signage or markings, difficult departure arrivals, faulty malfunctioning nav aids such as the ILS or PAPIs. Almost half of all threats logged can be attributed to ATC and adverse weather. However, the low error rate is an indication that crews were doing a good job in managing these threats. This table describes the number of threats encountered by our crew in terms of phase of flight. You will notice that the majority of threats, around 60%, are encountered were encountered during the pre-departure, taxi phase, and descent approach and landing phase of the flight. These results corroborate with a study of aircraft accidents conducted by Boeing some time back. The so-called sterile cockpit rules should be closely adhered to during these phases of flight so that crews may manage it appropriately. The table also shows that over 60% of threats were not cognitively planned for by crews. Therefore, standard operating procedures were adjusted to guide crews into briefing external threats more adequately. The next table describes the threats which were inconsequential versus those which were linked to a flight crew error. Interestingly enough, the majority of threats which resulted in error stemmed from cabin crew threats. It appears that flight deck crew are nevertheless handling both distractions and errors by flight attendants during pre-departure and takeoff relatively well. However, during a critical phase of flight, that is the approach and landing phase, it appears that other cabin threats such as trivial crew discussion or arbitrary paperwork are causing a weakening in the safety system. Moving to errors committed by flight deck crew, the graphic shows that the majority of errors were from briefing, automation, and manual handling of the aircraft. Briefing errors are regarded as procedural errors and can be items such as briefing completed late or incorrect or incomplete approach brief, while both automation and manual handling are categorized under aircraft handling error. An example of an automation error is the wrong altitude entered into the flight management control unit or computer, while a manual handling error could be excessive brake use. A total of 346 errors were logged by the SA LOSA observers. This slide is an example of how one can go deeper into the LOSA data set with more advanced statistical methods. In this case, we use students' t-test to compare groups. We compare the number of errors between captains and co-pilots. The data indicated that on average, captains committed 1.08 errors per sector and first officers 1.09 errors per sector. However, the basic t-test determined that these differences are not statistically significant at a 95% confidence level. So what does this all tell us? Well, what the statistics suggests is that no single group is responsible for more errors being committed than the other. In other words, it can be confidently established that crew members are effectively backing each other up. This is another area of strength within the operation which LOSA has highlighted, or is able to highlight. What is interesting from this error table is that it indicates that the Airbus fleet are committing errors with regard to automation, whilst the Boeing fleet are committing manual handling errors. One psychological hypothesis for this phenomenon is that the Boeing fleet seem to pride themselves on the fact that the aircraft is still more of a pilot's aircraft and they fly manually more often. So statistically, therefore, this would result in more manual handling error incidents. As you can see from this table, there were 174 threats, or the error to threat prevalence for the Airbus fleets were below the global norm, and just the freighter fleet exceeded the global norm for error to threat prevalence. A number of recommendations were made with the data gained from LOSA. Overall, around 50 to 60% of the LOSA recommendations were implemented. I'll mention just a few to give you an idea of what it could look like. Number one, a recommendation was that initial exposure to Airbus should be on the A320 family. South African Airways seems to be moving in the direction of an all Airbus narrow-body fleet. The automation philosophy on the Airbus family is understood better if the crew member has maximum exposure to the concept. That is best achieved on the narrow-body fleet, which entails multiple sectors and operating the aircraft under varying conditions on a daily basis. It also allows crew to experience the benefits of automation as well as the correct approach to manual handling. Improve communication with ATS authorities. With increased air traffic loads into airfields and airspace with limited capacity, there's a tendency for air traffic control authorities to reduce track miles, which can result in aircraft in a hot and high condition. Increasing fuel costs, however, meant that reduced track miles can be beneficial. It is also important that SAA flights operate at optimum flight levels at all times. Better communication with ATS authorities could therefore facilitate this. Change the stable approach criteria. In this case, criteria create a stable approach risk management profile which allows the go-around decision to be analyzed by the crew at 1,000 feet RA, or radial altitude, and finalized by 500 feet. So the LOSA actually picked up that to optimize the operation, reduction in the stabilized criteria would be still within the safe envelope. Establish a fatigue refresher training syllabus. With the advent of ULR city pairings, it is essential that an effective FRM section is established that feeds information to the crew members with respect to fatigue management training. The cabin crew should be exposed to the basic techniques, but all the risk in an ULR operation is carried by the flight deck crew, and this has to be recognized and managed as such. The concept of LOSA must have buy-in from all concerned parties. So in summary, such as the pilots management, unions, and other supporting departments within the airline. The quality of the observers used for the data gathering is critical for a successful LOSA. The unobtrusive nature of the typical LOSA observer is one such characteristics. Data obtained from the audit should be handled with care and scrutinized for inaccuracies or for accuracy. The quality of this evidence will add to the acceptance of recommended changes and the implementation of future LOSA projects within the airline. Dissemination of results to line pilots is absolutely critical in gaining trust for any future LOSA implementation. Communication thus completes the feedback loop. And thank you for your time, and that's the end of the LOSA presentation.